Alright, so today we pick up where the Greeks left off some 3,000 years ago. So Archimedes, the famous mathematician from Athens, had this crazy idea that he was going to try to find the area of the circle. Yeah, back then even that was a huge challenge. But some things are always the same. The human spirit is always indomitable, always searching for solutions. Here's a little picture of the human spirit 3,000 years ago in Athens. Archimedes says, you know what, circles are too difficult. I can't handle them. But I can handle triangles, so I'll make a triangle out of that, and I'll make a couple more triangles out of it. And I'll make a couple triangles, and I'll estimate the area of the circle by just making triangles. He called this the method of exhaustion because he got tired of making so many triangles. And he said, hey, that's pretty good. I'm good with triangles. I can find out this length. I can find out that length. I can do some little mathematics to figure out that. But that still leaves me an error here. An error, little wedges between the triangles and the circle. So he had this brilliant idea that he was going to undo that. And then instead of doing those type of triangles, he would do smaller triangles like this. And smaller triangles like this. You can see why it was called the method of exhaustion. Because he really got tired of it because there were so many of them. And that problem was not completely resolved until some 2,000 years later in the 17th century, when we have the Ninth Symphony, one of the 9 symphonies, the fundamental theorem of calculus. Today, we've got enough tools to tackle this problem. Not in the ultimate form that we will settle in, but we have enough tools to take a little peek at it and take a little crack at it. What this means concretely is that I tell you the first day how the reasoning goes for this class. The idea was that excuse me, the areas are ubiquitous. Everywhere you have a base times a height meaning something meaningful, you've got an area problem. And everywhere you have an area problem, you have a slope problem. We've done this to death. We've got enough tools where we could tackle this problem that we promised at the beginning. We promised that we were going to take some area, some crazy area like this, an area for gods or area for not for little kids, and we're going to cut it up in infinite little pieces. Each of the little pieces we can do, but they're really close to zero, and we're going to add them all up, even though there might be infinite many of them. We're ready for that. Riding the bull stuff. That's a really nice place to be. That's why today's a very, very, very special day. We're tackling some big and bold and brilliant ideas. And it's not even the end of it. Today's is just a little piece of it. Wait till you see what's coming up next time. Next lecture. Next lecture probably. I'm thinking the next lecture or the one after that will be the 9th symphony of the 17th century, called the fundamental theorem of calculus, where we will resolve the same problem that we're doing here today, but in a way that's 1,000 times more elegant. This is just a little preview, but even today is huge. So put your thinking cap on, turn off the TV, say bye to the wife, say bye to the boyfriend, focus your mind right here. Okay? Kick the cat out of the way. I'm just kidding. No letters. Anyways, so today's a huge day. We're ready for some big and bold ideas. Just real quickly, some of the ingredients that will go into this is we've got to have a really good good grasp on the famous properties that we talked about last couple lectures. Famous properties, and I believe we also did famous sums. The geometric sums, the sum of the n's, the sum of the n squares. These are going to be a crucial part of our partial solution to the big and bold idea. Clear? So if you haven't done that, make sure you review that, done the self-quiz, done the homework, posted questions. Alright, so I thought we could start off finding the area of something simple like a triangle. Even though we know how to do this by using just base times height over 2, we want to do it using the techniques that were started some 3,000 years ago and see how it goes. Because ultimately, the techniques we learn here are the ones that we're going to use to find the area, for example, under a curve like this. Really, that's all I want to do today. I don't want to do too much, but I want to do it really well. I want to find the area under this curve. I'll pick some segment here. And also, I want to find the area under this curve, curvy curve. By the way, curve is usually used for just a function, but even though sometimes the curves are not really curvy, they still call them curves, under the curve. Okay, so sometimes curve doesn't mean curve, whatever. So that's the game plan. The game plan today is to find out the area under this curve and also find out the area of this curve. But not just find the area, but develop a method. A method similar to what the Greeks started some 3,000 years ago. That's why I think it's an exciting day. Alright. I'm ready. Kind of nervous, man. I hate being nervous, but I'm excited. Let's do it. So before we go on cutting things up into infinitely many pieces that are infinitely small and adding them all up with great elegance, why don't we just start off with cutting things into, say, a few pieces. First off, let's define our parameters here. We're going to define the area under the curve. We'll say from here, from x equals 0, and I'll go all the way up to, say, right here for x equals 6. This is the area that I want, right here. And first, before we go cutting it up into infinitely many pieces that are infinitely small, why don't we cut it up into just a finite number of pieces? Let's say 6. Since this interval is 6 units long, it'll break up nicely if I just break it up into 6 pieces. Right? And each of these pieces, I'm going to take a rectangle out of it, a rectangle approximation of the curve. I could take this rectangle, that would be called the lower sum, or left sum, or I could take this rectangle, that would be called a right sum, or an upper sum. I think for now, I'm just going to go with the right sum. Most people do either one or both. It's overkill. Let's just do the right sum. And for this little rectangle, I'm going to keep consistent with the right sum. And for this one, I'm going to keep consistent for the right sum. And for this one, I'm going to keep consistent with the right sum. And for this one, I'm going to keep consistent with the right sum. And guess what I'm going to do on the last one? You guessed it. I'm going to keep consistent with the right sum. What I've done here is I've taken the sum and I broke it up into little pieces. I'm going to call this piece the first area, or A1. A2 for the second area. And I guess what I'm going to call the next one? You guessed it, A3, A4, A5, A6. I have 6 little areas, each of which is pretty doable because it's just base times height. And I'm going to break it up and I'm going to say, hey, you know what? My 6 little areas, I'm going to use that for 6 little areas, would be the sum of all the little ones, AK, as K goes from 1 to 6. K goes to 1, that would be A1, the first little area. K equals 2, that would be A2, the second little area. This is just a fancy way of saying A1 plus A2 plus A3 plus whatever, all the way up to A6. Okay, that's just a fancy way of saying it. But I want to write it in a fancy way because I want to develop the patterns and the ideas so that next time I don't just take 6 little areas. Next time I want to take 100 or 1,000 or 5,000 or 1,000,000. That's why I want to write it in this nice little pattern way. We're using the sigma, using the professional notation. Capiche? Alright, talk is cheap, let's do it. I say we go bold and we find the first little area. Let's say find A1 right here. How would you go about finding A1? Again, I don't really care about the actual area. I would care about patterns. What sort of pattern would I have to think about so that I could get all the A's? Let's think about A1. A1 is the base times the height. Now how would I calculate the base? To calculate the base, I would have to be thinking about something like this. This is called my base bubble. Here's how I would think about the base. I'd have an interval. The interval is from 1 to 6. From 1 to 6 is the interval. Sorry, I correct myself. From 0 to 6. And I want to cut it up into 6 pieces. So therefore, each piece is the interval is 6 units long divided by 6. So each piece is 1 unit long. That would be the width. And I do it this way. I know it's obvious. It's 1. Each one is 1. I do it this way because next time the interval may be from 0 to 7 or from 0 to 13. And I may want to cut it up into 25 pieces. And so I would have to do the interval, which would be whatever, divided by the number of pieces. That's the width. Here, I'll put an extra bubble here. It might be obvious, but I think it's worth stating. The width would be the length of the interval. Length of the interval all over the number of pieces, number of partitions, number of rectangles. How's that? Okay, so that gets me the pattern, so the next time I can do more with it. Okay, so the width is equal to 6 over 6. That's equal to 1. Check. How about the height? For the height, I'm going to make very, very important use of the fact that the function is f of x equals x over 2. Because when I look at the 1, which is the x value, I plug that 1 into the function, and that's what gives me the height. The first little height would be, I'll make a little error here. The first little height would be equal to f of 1. And so therefore my first little area is equal to f of 1 times 1, which is height times width. And I can even do better than that. I know what the height is. If I plug in 1 there, I get 1/2, and then that gives me the height, and then times 1, which is the width. There's your A1. Okay, let's go on and find A2. The width again is equal to 1, and the height would be f of 2, which would be whatever. You plug in 2 there in a function, that would be 1 times 1. But again, it might not be a good idea to write it at 1 times 1. It might be better off to plug it in there 2, so you can see the pattern here is 2 over 2 times 1. That's better, because if you simplify too much, you hide the patterns. A3 would be this one right here. The width is 1, and the height would be f of 3, which would be 3 over 2 times 1. And so on and so forth. The generic one, AK, would be 1 times f of k. And so that would be k over 2 times 1, which is just k over 2. That's the generic rectangle. And what I want to do is add them all up. So I'm going to clone this page here. Clone it, and then I'm going to erase everything. Just get rid of everything. Because all I want to do is focus on my work here. Let's work with this one right here, and the fact that all right, let's take it from there. So the area for 6 little rectangles would be the summation of all the AKs, and I've got a formula here for AKs is k over 2 as k goes from 1 to 6. Yeah, stop me if I'm lying. That's the width times the height. The width is 1, the height is f of k. That's 1 times k over 2. That's what it is. And that becomes, I could pull the constant out, so that becomes 1/2 times the summation of all the k's as k goes from 1 to 6. And that becomes one of the famous formulas. Remember that one? That would be this one. The summation of all the n's as n goes from 1 to p. That is exactly the same format as this one. The summation of all the k's from 1 to 6. So the grand total would be 1/2 times 6 times 6 plus 1 all over 2, which would be a grand total of 1/4 times 6 times 7 is 42. There you go. That would be the area if I cut it up into 6 pieces. But of course, that was just practice. So in other words, 42. Let me see. I can simplify that. That's 21. 21 over 2. So that's 10 and a half. So if I was to add up all these little rectangles, I'd get 10 and a half. 1, 2, 3, 4, 5, 6, 7, 8, whatever. 10 and a half of these little boxes. Clear? And that's all right. That's what the Greeks started, but it's not. There's some problems with it. Here, I'll point out what the problems are. The problems are right here. I'm going to point them out in red. That's a problem right there. 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 That's a problem. That's a problem. Those are problems. Those are errors that came from estimating the area, which wasn't a rectangle, and we tried to estimate it with a rectangle. That caused us error. And of course, the brilliant idea from the time of the Greeks was, hey, cut it up into more pieces, because if you cut it up into more pieces, imagine this. I'm just going to imagine what would happen if I cut it up into more pieces. Let me just give you a picture of what it would look like. I'll cut it up like that. I'm going by halves now. By halves. Look at the error now. See, the error is much smaller. For every one of these pieces, before the error would have been, for example, let's take a look at this piece. Before the error, the one I highlighted in red before, that would have been the whole thing here. Everything here would have been error. Now there's a lot less error. Now the error is only this piece right here. See? Which one's got more error? I told you. The more you cut it up, the finer your partitions here, the smaller your error. So, the next natural thing to do would be, hey, if cutting it up into 6 pieces was good, why don't we cut up into 20 pieces? Huh? Are you guys afraid or what? Just cut it up into 20 pieces so we can reduce the error. So I got a whole bunch of pieces here. 20 of them, and I'm just going to draw a couple of them because your mind and my mind are way too precious to waste on grunt work. I'll just draw a couple of them, and I'll underline here. Oh, can you see that or not? I'll underline here 20 pieces, 20 rectangles. Okay. And now my goal is to find out the first one, A1. Can I find at least the first little area? Can I find the width times the height? The first little width, well, that would be the whole interval, which is 6 divided by 20, because I've cut it up into 20 pieces. That's the width. How about the height? Well, this distance right here, that distance would be determined. That distance is 6 over 20, and to figure out that point right there, the first height, I would plug in my 6 over 20 into my function, and then that would be by A1. How about A2? A2 would be 6 over 20, and what would I plug into the function? Well, for that, let me take a little detour here so I can explain that. If this is 0 and this is 6 over 20, what would the next one be? Every one of these pieces 6 over 20 and 6 over 20. The next one would be 6 over 20 times 2. Two 6 over 20 pieces. And if I add another 6 over 20 pieces, this one would be 6 over 20 times 3. You get it? Every one of these pieces, you just add 6 over 20 times another one, times 4. That would be equivalent to adding another 6 over 20 piece to the previous one. So for the second one, I'm trying to find out this height here. I gotta plug in this value right here into my function, so that would give me the second height. This would be A2. A2 would be the width, 6 over 20, times the function f of 6 over 20 times 2. And again, I don't want to simplify this. I know you've been told all your life, you gotta simplify, you gotta simplify. And that's what happens when your high school wrestling coach is teaching your math classes. You don't have to simplify. In fact, if you simplify here, you hide the patterns. I'm telling you, it's best not to simplify. Okay? So I'm going to get all the PE coaches mad at me. What shall be, let it be. The truth will set you free. Bring it on. Come on, coaches. I'm just kidding. So easy to say this when I'm in the camera, behind the camera. Alright, I digressed. That's how you'd plug in your A2. So here we go. Where was we? Where were we? We were right here. Chugging along. So A2 would be f of 6 over 20 times 2. What do you suppose A3 would be? It would be 6 over 20 f of 6 over 20 times 3. That would be my next x value that I would plug in to get the height. And this is a nice way of writing it, because you can see the pattern. The kth one would be 6 over 20 times f of 6 over 20 times k. And that right there, that's what it's all about. Because once I've got the pattern, oh my goodness, once I've got the pattern, it's all over. Because now I can do this. If I take my area and I take 20 rectangles, that's the sum of all my little areas, starting with 1 and stopping at 20. And I've got a nice little pattern for that one. That's equal to starting at 1, stopping at 20 of 6. That's a 6 over 20. That's my width. F of 6 over 20 times k. That's the kth little area. And then I can do some more simplifying here. Keep in mind, we had that f of x was equal to x over 2, right? So therefore, this one becomes, let me think, I could factor that out. Well, I'll factor things out later. K is equal to 1 over 20 6 over 20 f of, I'm going to use f because I already know it anyways. I'm looking at it right here, x over 2. So f of blah is blah over 2. So f of that would be that over 2. That's my function. Again, f of blah is equal to blah over 2. Right? So f of this thing would be that over 2. Then I could clean it up some more. Now I think it's cleanup time because I'm thinking a couple steps ahead. I'm going to clean this number out. This number's got to be pulled through the sigma, and then I'll just have the sum of k's, which will be a piece of cake. So I think this is summation. I'll do it here. Summation of 6 over 20 times 6 over 40 times k. And that summation of 36 all over 8 with 2 zeros k. That would be the summation of 36 over 800 as k runs from 1 to k. Sorry, we're doing 20, right? Man, that looks so terrible. That's not the kind of teacher I am. That's funny. If that's not the kind of teacher I am, why do I always do it? 36 over 800 be super good. Summation of all the k's is k runs from 1 to 20. I did this 6 times 6 is 36, 2 times 4 is 8 with 2 zeros. Pull it out, simplifies for the birds, and now I've got something nice. I got something nice because here we go. I'm going to do 36 over 800 times summation of all the k's is k goes from 1 to 20. That's a famous formula. 20 times 21 all over 2. There you go. We did it. What is that number equal to? Who cares? It's just some number. It's the ideas, the beautiful ideas that count. The numbers, those numbers are for work on Monday morning. The ideas are for awesome, relaxing, meditating time on Sunday morning when you're drinking your coffee. Ideas, Sunday morning. The actual number is for Monday morning for work. Forget that. I'm not into that.